Hi everyone, I'm Chun-Jung, a PhD candidate at Australian Institute for Machine Learning. I'm going to present our WACV 2026 paper SceneEdited in this video. In the SceneEdited dataset, we want to raise a question is about can RGB image be used to update or correct highly accurate yet outdated HD map? Here, I will step by step to introduce each section in this poster. First of all, motivation part. HD maps are critical for autonomous vehicle driving. It can be seen as a sensor input providing occlusion information. Where is the traffic light and what will happen in the next intersection? However, our world changes rapidly, which will bring large number of change while self-driving car operating. For localization task, some change can be ignored, but some change will bring critical safety issue. For example, if a newly built building is seen by onboard sensor, but that particular building cannot be seen in the map, which will bring a question is, can self-driving cars still localize themselves in the map? And we will demo this particular scenario in this poster. On the left-hand side here, we localize black scan point into up-to-date HD map point cloud. On the right-hand side, the scan point will localize in an outdated point cloud, where the outdated point cloud don't have the corner building information. And let's view the up-to-date localization first. So here it runs pretty smooth and perfect, and let's view from the right-hand side. The pole point here will have the wrong post estimation because there's too many wrong correspondence at this area. To further see the impact of outdated point cloud, we stack scan point by the post estimate by previous localization video. And as a result, turn into this bottom row. And in here, all point is colored by the scan index, which means the point from the same scan will have the same color, and the point from a different scan will have the different color. And we will see here has getting blur at this pole area. And if we zoom in into the pole area here, we will see this result. On the left-hand side here, the width of the pole is 25 cm. And the right-hand side here, because of the localization error and wrong correspondence, the width of this pole is becoming 80 cm, which at least have 50 cm stiffness. And that will bring some safety concern to the self-driving car. As a result, regular update for HD map is needed, but current LiDAR-based update is hard to scale up, even it will bring some accurate result. And usually, to build a mapping car, it usually takes 1 million to one vehicle. In contrast, cameras are a scalable solution because of the price, but it has many challenges need to solve. Moreover, even there are many train detection algorithms and dataset exist. Only a few papers explore the next step to utilize this change map into the map updating, which is a visible gap between the train detection and map update. So we create this dataset for 3D map maintenance called SceneEdited. Next, let's move on to the next section about how we design this dataset to support 3D map maintenance. We designed two databases storing scenes and patches. For each scene in the scene database, we'll have one ground truth up-to-date point cloud map and many outdated versions waiting for update. The other database is patch database. We store many roadside infrastructure point cloud that have been cleaned manually. Each object is stored under its category. Some categories are like sign, stop sign, bollard. And here we show the automatic way to generate the outdated version from the ground truth. First thing is for the edit one. So edit here is mean we automate adding some patches into the up-to-date point cloud, and we store where we added the object and which points we insert into it. So after adding into it, it will generate outdated version that contain many outdated objects need to be cleaned up, they need to be removed, that will meet to the up-to-date one. And for the deleted one is your challenger. That means some object in the up-to-date, but it cannot be seen in the outdated version, such as In the up-to-date, it has this yellow point in the blue bounding box, but actually in the outdated version 1, it doesn't have this point. And we are explicitly asking image to recover this stop sign point cloud. We also provide some manually way to customize the outdated version. So here, the manually removed version is denoted to this version where this building point is missing, and these building points are selected by manually. Originally is here, and now it's become to here, and only have the left ground point left. Also, we store this change version by an efficient way. We do not explicitly store every point, but we store the change part. So the toolkit will help to, given this change information and the ground truth, it will generate this point cloud automatically. Except many point cloud tool, we also provide tool that retrieve the point index in a point cloud onto a pixel in the image plane. And also, this tool can help us to project the point cloud into image plane to get a depth map or point map. And by these point map and depth map, we can automatically infer the change map as well, such as this manually removed building is missing from here, and here is the change map region. Next section is going to talk about some existing methods that can generate image point cloud and what kind of challenge will this method face. Here we show a simple method like how we utilize this image to 3D point cloud predictor and how we calibrate them to meet the real metric point cloud. So here this image to 3D predictor are VGGT, duster, and master. The input will be the image sequence, many image, and you will get in this point cloud. And then we do the alignment on the unchanged part to estimate the scale, rotation, and translation to let this image point cloud to align onto the point cloud. After this pipeline, the result is on the right hand side. The first one is duster. The duster one, it has some floating point connecting the foreground object and the background object. The floating point is happening over here. And for the master, it has some page-like texture on this building, which will pollute the quality of the LiDAR point cloud. And here is the VGGT. VGGT here has the alignment issue. Like the black pole here, it should be aligned on the brown one here. So each method has their own issue and has many challenges need to be solved, need to be faced. To further analyze the performance of map updating, we compare the change part only by using this form. And so here, the black one is P-edit, which is contributed by duster, and the brown one is by the ground truth, which is the change building, the missing building it need to be covered. So we compare here. Here is the duster one, and here master and VGGT. And next we get this matrix. The DC one is transfer distance, and ADH is Hausdorff distance, which is the maximum point distance, and MH is modified Hausdorff distance, and DMP is median point distance. We also report the runtime. Last but not least, all demonstration like here, image, point cloud, and image to 3D predictor are taken from this city corner. And let me show the background. Here is Miami City in the Florida state. In this corner and this whole city scene are just a small snip in this SceneEdited dataset. At the end of this poster presentation, here we provide a QR code for link to the project webpage. The project webpage provides some paper source code and documentation for data instruction and toolkit instruction. Feel free to reach out me on WACV's venue and on the GitHub.